Okay, today we are continuing in our modeling and regression unit. Today we're going to be talking about more modeling data and modeling exponential growth and decay problems, specifically without a calculator. All right. I was going to call this topic modeling without a calculator, but there are some problems where I'm going to want you to use your calculator, so this is what I decided to call it. Alrighty, we're just going to dive in and take a look at some examples of some problem, doing some, answering some questions with or without a calculator. And in each of these, I'll tell you whether you get whether you have access to your calculator or not. All right, for number 1, a pump removes water from a tank for 24 hours one day. During this time, R of t, the rate of water removal in liters per hour at time t hours, is recorded at various times and shown in the table. Okay, no calculator, so I'm not going to be putting this in my calculator. From time 3 to time 8, what is the average rate of change of R? Average rate of change of R. The rate that water is being removed from the tank. Okay, average rate of change. As soon as I see that, I think change in R over change in the x coordinate, or in this case the t coordinate. Change in R over change in t. And they're telling me what the change in t is. So this will be R at 8 minus R at 3 divided by 8 minus 3. R of 8 is 670. R of 3 is 950. Okay, 8 minus 3 is 5. 670 minus 950. Well, 0 minus 0 is 0. 15 minus 7 is 8. 8 minus 6 is 2. And that's going to be a negative 280 over 5. And then 5 goes into 28 5 times with 3 left over. 5 goes into 36 times. So this is negative 56. Negative 56. Now, they asked me to indicate units of measure. So what would the units of measure be for that? Well, let's think about where this negative 56 came from. It came from change in R over change in t. R minus R, that will have rate units. T minus t, that will have time units. So we need rate units divided by time units. So I'm going to write that as liters per hour per hour. Liters per hour per hour. You could also write this as liters per hour over hours, because t is on the bottom. Liters per hour on top, t on the bottom. Or you could call this liters per hour squared, or even liters per hour squared, like that. Any of those would be acceptable unit responses. Okay? Part B. Using the average rate of change determined in Part A and the value of R when time is 8, approximate R of 10. Okay? So we're going to use this point and this rate to approximate R of 10. Okay? When you find an average rate of change, you are finding the slope between those 2 points. You're finding the slope from one point to another point. Okay? That's the slope. So we want to approximate R of 10 using that slope and that point. So I'm going to set up point-slope form for the equation of a line. In my mind, I think y minus a y coordinate is equal to a slope times x minus an x coordinate. That's in my mind what I'm thinking. But we don't have y's here, we have r's. So this y will be r at what I want it to be. I want it at 10. This y will be r at what they tell me to use, r at time 8. M is the slope, the average rate of change that they told me to use. And then x is the time that I want, and x sub 1 is the time that I know. This is what I'm setting up. And now I have r at time 10 minus r at time 8 is 670 is equal to negative 56 times 2. So r at time 10 minus 670 is negative 56 times 2, let's see, 12, carry the 1 is 11, so negative 112. And now I'm going to add 670 to both sides, right? So we'll have negative 112 plus 670. Got to simplify that for AP Pre-Cal. We have to simplify that. Let's see. 0 minus 2. 10 minus 2 is 8. 6 minus 1 is 5. 6 minus 1 is 5, and it's positive. So now I have one thing to change here. One thing to change. We are only approximating. We are only approximating. We don't know exactly. We're only using the slope between these 2 points to approximate a point after that. So these are not actual values. So I'm going to go back and I'm going to change each of these to a little approximately equal instead of equal, because I don't want to say anything that is not true. I can actually leave this as an equal to, because that is just simplifying this. So, but this is an approximately. So r of 10 is approximately equal to 558 liters per hour. Okay? All right. Okay. Certain situations are, I want you to think, are clearly exponential or logarithmic in nature. We just finished our unit on exponential and logarithmic functions. So I need you to be able to recognize situations like that. Okay? So in these situations, we're going to set up this function and then find a and b. Let's take a look. The initial population of bunnies in a park is measured to be 10. So we start with 10 bunnies in the park. And it is observed that the population doubles in size every 6 months. Let's think about that. If I were to write a little chart, a time versus population chart, I'm starting at, well, at time 0, I have 10 bunnies, yeah? In 6 months, how many bunnies will I have? 20, because they're doubling. In 6 more months, I'm going to have double that. In 18 months, I'm going to have double 40 or 80, and so forth. Okay? So in 6 more months, I'll have 160 bunnies. Okay, here's what I want you to notice about this. The time is increasing by the same thing each time. That has a linear growth. But the population, what's happening to it? We're multiplying by 2 each time. There's your exponential growth. That's exponential. So any time you see a problem where it says it doubles every so often, or triples every so often, or quadruples, or is a half-life. It has a half-life of something, so it cuts in half every so often. All of those are exponential in nature. So we are going to set up an exponential function for this. So part A says determine a function that gives bunnies as the output value. Population of bunnies as the output value. And time as an input value. So the output value is going to be a b. I'm setting up a times little b to the t. Time is our input, b is our output. I'm setting that up. And now I'm going to find a and b. Alright? A and b. So I'm going to use a pair of points. And the easiest pair of points to always use is when time is 0. So if they are kind enough to give me time 0, then I am definitely going to use time 0. So I'm going to say when time is 0, what are the number of bunnies? Well, the number of bunnies are 10. I'm looking for A, I'm looking for B, but I know that t is 0 at the initial time. B to the 0 is 1. So this tells me that A is 10. So now I know that B is equal to 10 times little b to the t. Now I need to find little t. To find little t, I'm going to go get another pair of points. So I'm going to use the pair of points that is the next smallest, so 6 and 20. But you could use any of those pairs of points. I'm going to use 6 and 20. So I'm doing it when time is 6 months. The population is 20. T is 6. I'm solving for B. So I'm going to divide both sides by 10, and I'm going to get 2 is equal to b to the 6. And now I'm going to 6th root each side, right? Or you can call that 2 to the 1/6 is equal to b. So I have b is equal to 10 times 2 to the 1/6 to the t. Okay? Now, as a multiple choice question, we don't know what the 6th root of 2 is, so I don't have a problem leaving it like that. As a multiple choice question, what could they do? They could write this as two to the t over 6. Okay? So that's one option. Okay? All right. So there we go. There we go. And this will work. And you can always see if it works. If you put in 12 for t, if I put in 12 for t, I would have b is equal to 10 times 2 to the 12 over 6, which is 2. 2 squared is 4. That gives me 40, and that's what I know it has to be. You can always check your answers on these. Okay? All right, part B. Now we're going to write a function that gives time as the output value. Time as the output value. And x is the population of bunnies as the input value. So, when they tell you to do this, you are first going to do what we just did. You're first going to do that. Then you're going to take your answer, and solve for t. That will give t as the output value. Solve for t. Okay? And they tell me to make x the population of bunnies. So I'm just going to replace b with x. So x is equal to 10 times 2 to the t over 6. How do we solve that for t? I'm getting t by itself. I'm going to begin by dividing both sides by 10. So I'll have x over 10 is equal to 2 to the t over 6. Now what? Now what do we do? Well, my base is 2. So I'm going to log base 2 both sides. Log base 2 both sides. Okay? So I'm going to have On the left-hand side, I'm going to have log base 2 of x over 10. On the right-hand side, log base 2 of 2 to the t over 6 is just the exponent t over 6. And now lastly, I multiplied both sides by that 6. Okay. Now I have time, which they tell me to say that that is a capital T, so I guess I can do that. Time as the output value and the population as the input value. So if they told me what the population was, I could find the time using that equation. Okay, let's do another one. Number 3. The half-life of radium-226 is 1600 years. If you start with 100 milligrams of radium-226, how much is left after 20,000 years? Well, half-life. Every half-life problem can be written as an exponential function. So as soon as I see half-life, I think y is equal to a times b to the t. Okay, that's what I'm thinking. Okay, y is my amount of radium-226. That's my amount. T is time. So I need to find the values of a and b. So I'm going to start with what I am given. I am given that we're starting with 100 milligrams of that isotope. So I'm going to put 100 in for y and 0 in for t. If you like to denote it like that, that's fine. That's great. So b to the 0 is 1, so we've learned that a is 100. So now my function, my equation is y is equal to 100 times b to the t. Now I must find b. I have to find b. The next number that I know is, since the half-life is 1600 years, I know when time is 1600, how much will I have left? I started with 100, so in 1600 years, I'm going to have 50 left. Okay? So that's my equation. I'm looking for b. I'm going to divide both sides by 100. That'll give me a 1/2 over here is equal to b to the 1600. And now I take the 1600th root of a half, and that is b. So b is 1/2 to the 1 over 1600. And now I have my function. Y is equal to 100 times 1/2 to the 1 over 1600 to the t. To the t over 1600, and I'm going to write it like that. So that's 1/2 to the 1 over 1600 to the t power. I'm just going to write it like that. Okay? How much is left after 20,000 years? We're going to put 20,000 in for t. And here we can use our calculator, so I'm going to grab my calculator. Haven't used it since my residual plot. Okay, 100 times 0.5 to the 20,000 divided by 1600. So there will be 0.017, at least 3 numbers after the decimal point. I'm going to give another couple, but at least 3 after the decimal point. And that is how many milligrams are left after 20,000 years. Okay, part B, how long does it take the 100 milligrams to decrease to 5 milligrams? Okay, here's our equation. We want to know how long that takes to decrease to 5 milligrams. I could, since this is a calculator active problem, I could go to my calculator and graph this. But my original purpose for doing this whole worksheet was to allow us to manipulate these a little, these equations. So I'm not going to do it that way. I'm going to do this mostly by hand and use my calculator at the very end, just like I did this one. I'm not going to touch my calculator to the end. So I'm going to put 5 milligrams in for Y. I'm going to divide both sides by 100. 5 divided by 100 is 1 over 20. Okay, and at this point, my t is in the exponent, so I need to log both sides. I do need to log both sides. What would be the base of our log? We could use base 1/2. We could use base 1/2, and I think I will. I guess I will. My knee jerk is always to ln both sides. It truly is, because I know that in calculus we exclusively use ln's. So my knee jerk is to ln both sides, but we can log base 1/2 both sides. And then I would get log base 1/2 of 1 over 20 is equal to just the exponent over here. And then t is equal to 1600 log base 1/2 of 1 over 20. And now we get to use our calculator. Okay? So 1600 log base 1/2. I'm so used to doing natural logs, I forget where this log function is. Is it under F3? I think it is. No, it's not. It's under F2. There's log base. So number 5, log base 1/2, 1 over 20. So that's going to be my answer. I want to show you guys something. 1600. You can do this without going to F2. You can do ln of 120 divided by ln of 1/2. Same answer. That's how I would do it. If we had ln both sides, that's what we would have been typing into our calculator. Okay, so our answer is 6915.084, at least 3 digits after the decimal point. If you want to give more, give more. At least 3. Okay, number 4. Oh, by the way, so that isotope had a half-life of 1600 years. The isotopes that they use in nuclear power plants have much longer half-lives. That's what makes them so, that's the advantage of nuclear power. Okay, number 4, another calculator one. A 50 milligram dose of a drug is administered to a patient. 2 hours later, the amount of drug in the body is 37 milligrams. The amount of medicine M in the patient's bloodstream can be modeled by the exponential decay function, M here, A times B to the T, after how many hours, okay, this is worded poorly, after how many hours after the initial injection will the amount in the body be 1 milligram? How many hours will it be 1 milligram? Okay. So we have M is equal to A times B to the T. We need to find A and B. So initially, M is 50 milligrams. That's when time is 0. So I know A is 50. So now I know M is equal to 50 times B to the T. 2 hours later, we have 37 milligrams. So 2 hours later, the amount in the body is 37 milligrams. So that's my equation. Divide both sides by 50. Square root both sides. B is equal to the square root of 37 over 50. Or you could write that as 37 over 50 to the 1/2. Either way is fine. So we know that we now know the exact function for m. 50 times 37 over 50 to the 1/2 to the t, right? Yeah? Or you could write that as to the t over 2. Either way. Okay, we want the initial, we want the amount to be down to 1 milligram. We want to know how long will that take. So I'm putting 1 in for m. Divide both sides by 50. T is in the power, so I want to log both sides. This time I'm going to ln both sides. So I'm going to ln both sides, and I get ln of 1 over 50 is equal to, I'm going to pull the power to the front, so t over 2, ln of 37 over 50, which I'm going to divide over. Ln of 37 over 50 will be divided over, right? Power to the front, and then divide by what's with your t. And now I just have to multiply by 2. So t is equal to 2 ln of 1 over 50 divided by ln of 37 over 50. And to my calculator I go. Okay, 2 ln of 1/50th divided by ln of 37 divided by 50. 25.9844. Is that one of my choices? It is. So choice A is the correct answer. Okay. Number 5. All right, no calculator on this one. The next couple, no calculator. Okay, I got these from AP Classroom, or one similar to it. A decibel is a unit of measure for the loudness of sound. The decibel scale is based on sound intensity. N, so N is sound intensity in watts per hour. Oh, I'm sorry, watts per square meter. A decibel value is given by the function d. So d is decibel, where the decibel can be got if we know n. N is our independent variable. We can get d if we know n. What must be the sound intensity? What must the sound intensity be in order to yield a decibel equal to 90? That's about how loud a lawnmower is. So I'm putting 90 in to the decibel. So 90 goes in for D. So I'll have 90 is equal to 10 log base 10 of n over 10 to the negative 12. Okay. Now, ask me why they give this function like this. Why would you divide by 10 to the negative 12? The answer is, I have no idea. I am sure that there's a reason, but I do not know what it is. Okay? I am immediately going to move that 10 to the 12 up to the top, right? I'm going to divide both sides by this 10 and get 9 on the other side. And now I'm going to write this as 10 to the 12th times n. And all we have to do is solve for n. So what do we do on both sides? The base is 10, so I'm going to 10 to both sides. 10 to both sides, right? So I'll have 10 to the 9 is equal to 10 10 to the 12th times n. So divide both sides by 10 to the 12th, and we find that n is equal to 1 over 10 cubed, 1 over 1,000. A. Okay? Alrighty. Number 6. Again, no calculator. A disease affecting a certain type of fish in a lake is spreading at the rate of 13% per day. 13% per day. 50 fish are observed to have the disease on day 1. Which of the following functions give the number of fish that have the disease after T weeks? Ugh. I hate it when they mix up our units. Everything was in days, and now they want it in weeks. That stinks. Yeah? Okay. But what I'm going to do is I'm going to first think in days, because that's what they give me, and then I will try to think of it in weeks. Okay? So, it is spreading at a rate of this much per day. Again, just like doubling or half-lifing or whatever, it's not going in half, the rate is, it's spreading at a rate. So it's instead of doubling, it's only going up by 13% per day. Okay? Now, I'm going to come back, but I'm going to do this. Let's think about that. On day one, if I made a little T and fish with the disease chart, okay, on day 1, it says there are 50 fish that have it, okay? How many fish would have it on day 2? How many fish would have it on day 2? Well, the 50 who already had it plus 13% of how many already had it. So 13% of how many already had it. That is 50 times 1.13. This is our growth rate right here. Okay, 1.13. That means it's growing at a rate of 13%. If it was just a 1, it wouldn't be growing at all. It would be staying the same every time. Okay, let me do it again. On day 3, we're going to have how many already had it plus 13% times how many already had it. That would be 50 times 1.13 squared. Yeah? So this is in days. Okay? So our growth rate is 1.13. When you see 1.13, you know it's growing at a rate of 13%. Okay? What if it was doubling? Then it wouldn't be this at all. It would be a 2 there. It's doubling. Well, if it was tripling, well, then it would be a 3 there. Okay? So I know what my formula looks like in days. In days, my formula looks like the number of fish, I'll call it F, is equal to 50 times 1.13 to the T days. That's in days. Okay, what's going to happen in weeks? Well, let me ask you this. Let me go down to 7. It's 7 days. That's 1 week, right? In 7 days, how many fish will have it? 50 times 1.13 to the 7. Yeah? That's what we want for 1 week. So in 1 week, we want 50 times 1.13 to the 7. That's what we want. Which of these will give that to us? When T is 1, then, in these, which will give us that. C will give us that, right? Definitely not A or B, because they have the wrong factor there, or the wrong exponent. This one is close, but it doesn't have 1.13 to the 7. It just has 0.3 to the 7. So the answer here is C. That's thinking through it logically. Okay? All right. These are definitely thinking problems. So you need to spend a little time and make it make sense to you. Okay? Don't expect it to come to you immediately. Just spend some time.